electricity through a combination of gas turbines, steam turbines, and heat recovery systems. The operational challenge is that net electrical output varies with ambient and plant conditions. In this dataset, we have 9,568 hourly observations containing ambient temperature, exhaust vacuum, ambient pressure, and relative humidity. The objective of this project was to build a machine learning model that predicts net hourly electrical energy output measured in megawatts. This is useful because a reliable output estimate could support generation planning, operational monitoring, and more informed decision-making using sensor data already available at the plant. The final target variable is PE, or electrical output, while AT, V, AP, and RH are used as the predictive features. I structured the work around the 4 elements used in the project assessment. First, I define the modeling approach. Since PE is a continuous numerical variable, this is a supervised regression problem. I used all 4 available sensor variables as candidate features and selected RMSE as the primary evaluation metric. Second, I built and compared multiple models. I created an 80% development set and reserved 20% as an untouched test set. I then used 5-fold cross-validation on the development data to compare linear regression, gradient boosting, and random forest. Third, I evaluated the selected model. The final model was chosen using cross-validation performance only, and it was then evaluated once on the held-out test set using RMSE, MAE, and R-squared. Finally, I interpreted the model using actual versus predicted results, residual analysis, and feature importance. This helped assess both predictive accuracy and the main variables driving the predictions. The first decision was to correctly frame the machine learning task. The model has historical observations where both the inputs and the actual output are known, so this is supervised learning. Because the target PE is measured continuously in megawatts rather than as a category, the appropriate task is regression rather than classification. The 4 features are ambient temperature, exhaust vacuum, ambient pressure, and relative humidity. All variables were numeric, and the dataset contained no missing values. The dataset therefore required minimal pre-processing. I retained all 4 variables because each is operationally plausible and potentially predictive. The exploratory results also showed that ambient temperature had a particularly strong relationship with output. Specifically, AT had a correlation of approximately -0.95 with PE. This means higher temperatures were generally associated with lower output in the observed data. However, this should be interpreted as association rather than causation. To identify the best modeling approach, I compared 3 regression algorithms with different levels of complexity. The first was linear regression. This provided a simple and interpretable baseline and tested whether the relationship could be captured adequately using a linear equation. The second was gradient boosting. This model builds a sequence of trees, with each tree attempting to correct errors made by the previous trees. It can capture nonlinear relationships and interactions. The third was random forest. This model combines predictions from many decision trees, which helps capture nonlinear patterns while reducing the instability of a single tree. I reserved 20% of the data as an untouched test set. On the remaining 80%, I used 5-fold cross-validation. In each iteration, 4 folds were used for training and 1 fold for validation, and the process was repeated 5 times. This ensured that each model was assessed on multiple validation samples rather than relying on one arbitrary split. The cross-validation RMSE results were 4.572 megawatts for linear regression, 3.822 for gradient boosting, and 3.451 for random forest. Because lower RMSE represents better predictive performance, random forest was selected as the final model. Here we separate model selection from final model evaluation. On the left, the model selection results show that random forest achieved the lowest cross-validation RMSE of 3.451 megawatts. This was approximately 24.5% lower than the linear regression baseline, and also lower than gradient boosting. That improvement suggests the relationship between operating conditions and electrical output contains nonlinear patterns that linear regression does not fully capture. After selecting random forest, I retrained it using the full development dataset and evaluated it once on the untouched test set. The final model achieved a test RMSE of 3.231 megawatts and a MAE of 2.315 megawatts. The MAE means that, on average, the predictions were about 2.3 megawatts away from the actual output. The R-squared value was 0.964, meaning the model explained approximately 96.4% of the variation in electrical output in the test data. The test RMSE was also slightly lower than the cross-validation RMSE, which suggests the model generalized well and did not show obvious signs of overfitting on this split. The actual versus predicted chart shows that most observations lie close to the diagonal reference line. This indicates that predicted output generally tracks actual output closely across the full range of plant output. There are a small number of larger errors, visible as points further from the diagonal, but these are relatively limited compared with the overall pattern. The residual chart also shows that most residuals are centered around 0. That suggests the model is not consistently overpredicting or underpredicting. There are some outliers and slightly greater dispersion in parts of the output range, so the model is not perfect and should still be monitored if used operationally. The feature importance analysis shows that ambient temperature contributed approximately 90% of the random forest's calculated importance. Exhaust vacuum contributed around 6%, while ambient pressure and relative humidity contributed roughly 2% each. This is consistent with the strong negative relationship observed between temperature and output. The key conclusion is that random forest provided the strongest validated performance and predicted unseen hourly output with an average absolute error of approximately 2.3 megawatts. At the same time, feature importance reflects predictive contribution rather than causality, so the model should be used for prediction and operational support rather than to claim why changes in output occur.